Today I'll be reviewing AP Chemistry Unit 4, Chemical Reactions. So let's get started. So a physical change is basically when the composition of the substance does not change, while physical properties do change. Some examples of physical changes are shape and color, and there are some more there also. A chemical change is basically when a substance undergoes a chemical reaction and a new substance is formed. Some examples of this that you have to look out for during the chemical change is when heat or light is produced, there's a formation of a precipitant, or the gas is produced. So here's a problem with this. And so what we can see is basically it's asking us to find what hypothesis indicates that there's a chemical change in the reaction. So what we can do is we can just take out any answers that we feel aren't correct. So for A, if sodium is added to water, it'll dissolve. That is not a chemical change, as it still keeps its molecular structure. Well, it keeps its molecular structure, it's just has a phase change. If sodium is added to water, the total mass will be the same. That's not a chemical change. And if sodium is added to water, the water will remain a clear, colorless liquid. That's also not a physical change. So B. So B is basically if sodium is added to water, heat and light will be released. And that is true of a chemical change, as this is one of the criteria you get when making one of those judgments. So let's go on to 4.2, non-ionic equations. So balanced equations can represent physical processes, and a net ionic equation basically is when you remove spectator ions. It's a special type of a balanced equation. So let's try this first problem over here. So you have Ca3PO4, 2 solid, plus H3PO4 creates CaH2PO4, 2 solid. So let's just put out all the ions. So let's do Ca, H, and PO4. Got the H plus. Okay, so let's have it one side be the products and the other side be the reactants. So let's see how much calcium we have. So we have 3 calcium in the reactants and 1 calcium in the products. We have 3 hydrogens in the reactants and 4 hydrogens in the products. We also have 2 3 phosphates in the reactants and 2 phosphates in the products. So let's try to balance this out. So what we have to do is we can first start by taking out the lowest denominator, and that's calcium. So you can multiply this by 3. So 3Ca also has, so you have 4 hydrogens, so 4 times 3 is 12. And you have 2 PO4s is 6, which makes 6. So you have that. And so now what you have to do is you have to basically keep the calcium the same while changing the H3PO4, as calcium is already balanced. And so what you can do is you can multiply the H plus by 4. So 4H3 is 12. And 4PO4 plus, so you have 4 plus 2 is 6. So 6. So the coefficient for H3PO4 is 4. And on most of these questions, you have to be able to do this within a minute and a half at the max. So I would recommend just practicing these, as they're probably some of the easier problems that you'll get on the AP test. So that's the coefficient. Now we have another one. So the color of AgI, solid, a salt, silver is yellow. A student adds a solution of NaI to a test tube containing a small amount of solid cream-colored AgBr. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. So what we have to add is we have to create a net ionic equation. So we have Na, sodium, plus iodide minus plus I'm not sure if AgBr is soluble. I believe it's insoluble, so I'll put it as it being together. So what you have over here is it basically creates AgI, which is a solid, plus Br minus. Now what you have to do is, well, plus Na plus. Now, in order to remove spectator ions, what you have to do is you have to find the ions that don't have an effect in the reaction. So we can see sodium is a spectator as it basically plays no effect in the reaction, while Br is basically being removed from the Ag because it's a solid. So the solid becomes an ion. So that's why Br is still in the equation while Na is gone. So let's erase it out and just make it into I plus AgBr creates AgI plus Br minus. So that's our ionic equation. So 4.3, representations of reactions. So what we have is that like the subscript of a reaction basically just denotes the amount of hydrogens or the amount of that particle in one ion. So, and the coefficient just denotes how much of the ion is there. So in order to make like a ratio. So let's try this problem. So this problem is basically asking you to create a particulate representation of the dissociation of hydrogen peroxide. So let's try this over here. So what you have is four H2O2s. So two hydrogen peroxides creates two water plus one oxygen. So what you have is you have to create, since you have four, you have to create four H2Os. And then you also have to create four O2s. So let's just change the color to black. Okay. So we have four H2Os. So this is one O. And these are two H's. And then we have two, three. And so the reaction also creates one O2. So, well, after I finish the fourth one, I'm not too good at drawing. You won't be judged with your drawing unless like it's one of those problems which asks for you to specifically denote the position of that molecule, but most of them, they won't ask you to do such a thing. So you have four H2Os, and then you have O2s because there's extra oxygen. So what you have to do is you have to draw two O2 molecules. And this is all you have to do. So after this, you're done. So clear all drawings. Go to the four. So a physical process is basically when you involve a change in intermolecular attractions, but bonds are not broken when the substance undergoes a physical change. And like in the previous units, a physical change is when it changes phase or changes color or something like that. So let's try this problem on which of the following describes the changes in forces of attraction that occur as water changes phase from a liquid to a vapor. So for this one, what you have to know is that for changing a phase, it's a physical change. And in a physical change, bonds are not broken. So what we can remove from the answer choices is A, because it's saying the HO bonds break. C, C, as the bonds between H2O are broken, which is false. D, ionic bonds between H plus and OH ions are broken. And E, as covalent bonds between H plus ions and H2O molecules become more effective. So B is the correct answer choice, as due to the hydrogen bonds between the H2O molecules are broken, which shows that the molecules still they stay the same, but then they are changing phase. And that's basically what happens when H2O changes phases from a liquid to a vapor. So, 4.5, stoichiometry. So stoichiometry is basically the study of the relationships between the relative quantities of substances taking part in a reaction. Stoichiometry can predict moles or grams, such as limiting reactant, excess reactant, and theoretical yield, aqueous solutions, and gases. So let's try this problem with stoichiometry. So you have Fe, or iron, solid, plus 2 hydrochloric acid molecules, creates FeCl2 and H2 gas. So when a student adds 30 milliliters of 0.1 molarity HCl to 0.56 grams of powdered Fe, a reaction occurs according to the equation above. When the reaction is complete at 273 Kelvin and 1 atm, which of the following is true? So what this problem is an excess reactant problem. So what you have to do is, well, a limiting or excess reactant problem. So what you have to do is you have to get the limiting, which one's the limiting reactant. So let's try this. So you know that molarity equals moles divided by liters. So you have 30, wait, I'll change color, my bad. So you have 30 milliliters. So 30 milliliters and 1000 milliliters is 1 liter. And 1 liter. So molarity is moles divided by liters. So 1 liter is 1 mole. And that's what you're looking for. So 30 divided by 1000 is 0.03 moles HCl. And so with that, you have 2 moles of HCl. So 1 mole for 1 mole of iron. And so 0.03 divided by 2 is 0.015. Running out of space. So this is for HCl. So let's try for Fe. So the mass of Fe is 0.56 grams. So 0.56 grams times 1 mole of Fe is approximately 56 grams. So it's around 55.85, but you can estimate. So 0.56 divided by 56 is 0.010 moles. So we can cross out some answers due to knowing the limiting reactant. So as the HCl is excess, the limiting reactant is, actually, my bad. As the HCl is limiting, then the Fe is excess. So you can cross out the options A and B. And also, as C is showing that 0.015 mole of FeCl2 was produced, that's not true because there's only 0.01 mole that was produced. Then D is the correct choice due to elimination of all the other answers. So clear all the drawings. So let's do 4.6, titrations. So a titration is basically when you're using a known solution of a known concentration to find the unknown concentration of another solution. So this diagram shows a titration experiment. So the titrant is basically what you're titrating onto the analyte, which is in the volumetric flask. And the burette is used to put in small amounts of titrant into the flask. So the equivalence point is when the amount of titrant has completely reacted with all the analyte, and so the concentrations are equal. And the endpoint is basically when the indicator, which basically is used to determine the equivalence point, has changed color. So these two are different from each other. You could also graph instead of using an endpoint. So yeah. So let's try this problem out over here. So potassium sorbate K(C)6H7O2 with a molar mass of 150 grams per mole is commonly added to diet soft drinks as preservative. A stock solution of K(C)6H7O2 of known concentration must be prepared. A student titrates 45 milliliters of the stock solution with 0.1 to 5 molarity HCl. So write the net ionic equation between K(C)6H7O2 and HCl. So let's do that here. So you have K plus C6, sorry for my bad writing, H7, 2 plus HCl, as HCl is strong acid, so it dissociates completely. So that basically creates KCl. Cl minus plus HC6H7O2 as that's weak acid. So you can see that the K and Cl are spectators, so you can take them out. So KCl, and you could just erase them. So all you have is C6H7O2 plus water creates HC6H7O2. So now part B. So a total of 29.95 milliliters of 1.25 molarity HCl is required to reach the equivalence point. Calculate the concentration of Kc6H7O2 in the stock solution. So what you're trying to do is you have to use this equation called M1V1 equals M2V2. And so you know the amount of HCl, the molarity and the amount of HCl. So you can do 1.25 times 29.95 equals 45, or M1, 45. So then what you have to do is you have to divide both sides by 45. And it's about 45. So these two cancel out. I'll erase it. And that's M1. So you can plug this into your calculator and you will get 1.25 times 29.5. That's 37.43 divided by 45. And that's around M1 equals 0.832. For the AP test, you just need to put 3 sig figs, as that will basically give the point. So I would work to try to get sig figs though, but 3 is required if you don't know what you're doing. So that's the amount. So let's do reading a burette. So when you read a burette, the meniscus is basically this whole line thingy. And so what you have to do to read it is you basically have to read at the end of the meniscus, or over here, as that's where it'll be the area. So let's try this over here. So write down the initial and final reading and use them to determine the volume of KMnO4 that was added during the titration. So what you have over here is it's asking us to basically find the amount of Km and O4 that was in the initial and final. We use the burette to find it. So basically what you have is it goes from 3 milliliters, so 3.1, 3.2, 3.3. And look, it's somewhere between 3.3 and 3.4. So we can basically do a guess and make it like 3.35 to 3.37, I guess, something between that. I'll put it as 3.35. And also for this one, we have 29. And so 29.1, 29.2, 29.3, 29.4, 29.5, and it's between 29.5 and 29.6. So let's do it as 29.55. Now it's asking us to determine the volume that was added during titration. So you just subtract final minus initial, and you get 29.55 minus 3.35, and you get 26.20. So bam, here you have it. So 4.7, types of chemical reactions. So the first major type of chemical reaction that you'll see is a precipitation reaction. So basically, if you mix ions in aqueous solutions, you can sometimes produce an insoluble compound. In order to do these sort of reactions, along with any other type of reaction, you have to know your solubility rules. So let's try this first problem. A precipitate is formed when solutions of trisodium phosphate and calcium chloride are mixed. So let's try this. So it's asking us to do the ionic equation. So you have Na, 3Na plus PO4 plus Ca2 plus calcium plus 2Cl minus. And so basically what you have is, once you have the NaCl, you have to multiply by all of it by 3 and 2 in order to get 6. So you have 6 Na, 6 Cl minus, and let's change that. Here, 6 Na, 6 Cl. And so there would be 3 calciums for 6 chlorides and 2 phosphates. So that will create an insoluble solid, calcium phosphate. So Ca3PO4. 2. And the sodium and the chloride are spectators, so you can take them out and you can erase them. Oh no, my bad. Oh, it's 2. Okay, so let's do problem 2. 2 solutions of lead nitrate and potassium hydroxide are mixed together. So Pb 2 plus NO3 minus, well, 2 NO3 creates, not that, it's, you have to add it. So plus 2K plus 2 hydroxides. And so what that creates is PbOH, which is insoluble. And along with K plus NO3 minus 2K2NO3. So PbOH2 is our our main thing, and we have to take out the Ks and the NO3s as their spectators. So yeah. So this is what we have: Pb2 plus 2OH minus creates PbOH2. So clear all drawings, and let's go into 4.8 acid-base reactions. So with an acid-base reaction, so what you have is a Bronsted-Lowry acid-base reaction. So water can behave as an acid or a base, and when you mix an acid and a base, it creates a salt and it creates water most of the time. This the one over here is kind of an exception. So let's identify the acids, bases, and conjugate pairs. So the acid over here is HNO3. Well, I'll actually change color. So acids are red. So the acid over here is HNO3, and the base over here is H2O. So the base has a conjugate acid, which basically would be H3O plus. So that's also an acid. And the conjugate base of HNO3 is NO3 minus. So H2O donates, well, accepts a proton from the HNO3 to create H3O plus, while the HNO3 donates a proton to the H2O and becomes NO3 minus. So that's the acids and base. So the conjugate pairs are HNO3 and NO3 minus, along with H2O and H3O plus. Now, problem 2, what you have is solutions of ammonia and hydrofluoric acid are mixed. So we have NH3 plus HF, which is a weak acid. So what happens when you mix ammonia and hydrofluoric acid is you have an equilibrium reaction. So what happens is the hydrofluoric acid donates the proton to NH3, creating NH4 plus, and the F minus becomes the base. So this is the reaction of ammonia and hydrofluoric acid. So quit all drawings, and let's go on to finally redox reactions. So an oxidation reduction reaction is when electrons are transferred between the reactants. And so the substance that loses electrons is being oxidized, while the substance that gains electrons is being reduced. So an oxidation number can be assigned to each atom, and the sum of all oxidation numbers in neutral compounds is 0, while the sum of all oxidation numbers in ions is equal to the charge. So let's try practicing with oxidation numbers. So we know NaNO3 is basically neutral, so it'll have to equal 0. So Na has a +1 charge. So oxygen, when it's with the nonmetal, it has a -2 charge. So -2 times 3 is -6, and nitrogen has a +5 charge. So +6 minus 6 is 0, so charge of 0. Let's try this with SO4 2 minus. So oxygen has a -2 charge, so 2 times 4 is 8, and then sulfur has a +6 charge. So +6 minus 8 is -2, so that's our charge. And let's try an actual redox problem over here. So aluminum is mixed with aqueous copper 2 nitrate solution. So this is nitrate is a spectator. So you have Al, which is a solid, plus Cu 2 plus. And basically what we have to do is we have to balance it. So L3 plus Cu minus. So the substance that's losing electrons is getting oxidized. So the oxidized one is the one, so Al is losing electrons. So Al, so let's do O and then R. So Al becomes Al3 plus 3 electrons. And for reduction, you are gaining electrons. So you have Cu2 plus 2 electrons creates Cu, copper. And so you have 2 electrons and you have 3 electrons. So what you have to do is you have to multiply by a common coefficient. So 2 and 3 make 6. So you have to multiply this by 2 and this by 3. So what that creates is 3 Cu, 6 electrons, and then let me erase this. 3 Cu2 plus. And for aluminum, you have 2Al makes 2Al3 plus 6 electrons. And so you can basically take out the electrons and cancel them out. And so our equation, once we balance it, is 2Al plus 3Cu2 plus makes 2Al3 plus and 3 copper. So that's it. So I just enjoy doing this. So just one more page left and okay. So acknowledgements. So thank you to College Board for providing the problems. They're extremely helpful and they are great for providing them. And along with that, thank you to all of you for watching. And as this marks the end of the AP Chemistry Review series that I'm making, I hope you all do the best you can on the AP test. And most importantly, stay safe.